Okay, so let's look at our 10th lab now. So let's go to Blackboard here. Lab 10, a bit easier than Lab 9. And what we're doing in this one is we're going to be doing a 2D truss, but this time, instead of giving you guys some members, what we're going to do is let SAP go and design it. So it'll go and automatically pick the members from a subsection of members that we give it. So this is what we can use to go and do some automatic design using SAP2000. And I don't think you guys have had your steel or concrete courses yet, but this is really nice because instead of needing to iterate through all these different types of member choices when we're doing design calculations, it can go and do that automatically and find the most optimal member to use of the ones you give it. So we're going to be demonstrating this with a truss today, nice and easy. So we're going to consider the 2D truss in figure 1. All members are pinned at each end because it's a truss. Loads are acting in the direction of gravity. We're going to consider the self-weight of the structure to be present this time because we're kind of modeling a more realistic truss. And then using the steel design check tool, we're going to select the angle members for each element. And then all top chord elements should be the same shape. All the webs should be the same shape. And all the bottom chord elements should be the same shape. And why would we want to impose this constraint? Well, when we're building trusses, it's going to pick the most optimal shape for each and every single one of these elements. Now, if we're actually trying to build the thing, that's going to be kind of difficult if every single one of these is a different shape and we've got to make a unique type of connection at every single one of these connection points here. And that makes fabrication more difficult than it has to be. So generally what we try and do is we try and find the most optimal for a type of part of our structure here. So like for the bottom chord here, or the top chord here, or for each of our webs here. And what that does is it makes whoever's job who has to actually wind up building this thing a little easier, so they're not trying to play a big steel puzzle that has way too many different parts trying to fit together that are all different shapes and sizes. So make sense to everyone? Okay, so we're going to model ourselves a quick truss in SAP. So we've got 6 divisions of 4 feet and 3 divisions of 3 feet high. So we're going to make ourselves a grid that has 7 X divisions at 4 feet and 4 lines in the Z direction at 3 feet apart to go and draw this for ourselves pretty quickly. So let's go and open up SAP 2000. We're going to be using kips and feet as our units this time. And then we're going to click on grid only. In the X direction, like I was saying, we want 7 there. In the Y direction, we want 1 there. And in the Z direction, we want 4 there. In the X direction, that's going to be 4 feet. And in the Y direction, that's going to be 3 feet. Or sorry, Z direction, 4. Y direction doesn't matter. And Z here, that's going to be 3. And then the origin can stay at 0, 0, 0. So we've got 7, 1, 4, 4, 4, 3, and 0, 0, 0. Make sense? So let's say okay there. This is an XY plane view here, so I'm going to change that to XZ. And we see we now have a grid here that we can go and draw our truss as. So I'm going to go and click on the draw frame / cable here. We'll worry about the section stuff in a minute. We've got to do something special for that. So for now, we're just going to draw it as FSEC1, which is the default section, which is that W18 by 35 we just saw. But it gets the geometry in there. So for each bit of the top chord, make sure we draw those. Each bit of the bottom chord, make sure we stop at each of the grid points there. And, sorry? Oh, yeah. And then for each of the webs here, we want to make sure we draw it like that.
So on the bottom, we should click on every division.
Exactly, yeah. So because we have joints at every single one of these divisions between the webs, we want to make sure we have a joint at every single one of those and our members aren't continuous across them. Make sense? Okay, so our geometry should look like this. For supports, we want a pin at the left and a roller at the right. So let's select the left node there. Then we'll go to Assign Joint Restraints, click on Pin, say OK. At the right here, we'll select that one, then go to Assign Joint Restraints, click on a roller, say OK. And then in here, we have dead load and live load applied along the top chord of the truss. Now, if you recall, when we were talking about the definitions of a truss, we really should not be applying distributed loads or any type of loads along the truss member itself. In a true, pure theoretical truss that you can solve by just the equations of equilibrium at the joints, you can only apply loads at the joints. But when we start applying loads on the members in between, that's going to induce bending in the members. So it's not a pure truss element anymore. It's got some moment and bending there. And this is more realistic because, you know, in real life, we can't just only apply loads at these points here. This is something like a roof truss here. I mean, sometimes with like purlins and stuff, you can move the loads just to these joints right here. But a lot of the time, if you like have the deck board directly attached to the truss here, and you got all the roof loads on top of that, you're going to have load between your joints here. And they're all going to have self-weight as well. So they're all going to have a little bit of load anyway in between. So there's always going to be a little bit of bending in reality. Okay, so we've got dead loads and live loads applied on our top chord here. We're not going to be doing load combinations with this one. We're just going to do a dead load, 0.5 kips per foot, and a live load of 1 kip per foot. And those are applied on those. So let's make ourselves those loads. Dead load, we are considering the self-weight, so leave that as 1. And then we'll make ourselves a live load. And that's at 0, so we add that. So we'll say okay there. Okay. What's that?
The rest,
Yes. Okay. So let's select all of our top chord members here. We'll go to Assign. We'll go to Frame Loads. We'll go to Distributed. Now, for our dead load here, which is going to have a magnitude of 0.5 kips per foot, we'll say it's dead. Coordinate system's global. Load direction is in gravity. And then it's a force, so that's okay. Now, because this is an angled member and gravity is going towards -z, what it's going to do when we press OK here is it's going to have these kind of skewed distributed loads that are all pointing down in the direction of gravity. And that's exactly what we're looking for in this case. If you want it to be exactly perpendicular to the roof, there's ways to do that, where it's basically modeled as a combination of this and an axial load as well. Or this is basically a combination of that skewed and axial load. But this is pretty realistic, like what we'd get for like a snow load on the roof, or like the weight of the roofing material or something like that. So that was our dead load. We'll do the same thing again for a live load. So I'll press Control J to select everything again. We'll go to Assign, Frame Loads, Distributed. We'll change it from dead to live. And here we've got 1 kip per foot. Then we'll say OK. So those are our loads there. Before I forget, we want to make sure that we're considering this as a truss. So we want to release all of our members to go and make sure all of these are modeled as pins instead of fixed supports, or sorry, fixed connections. So we'll just say Control A to select everything. then we will go to assign, frame, releases / partial fixity. And we go and check these bottom 4 boxes here, press OK. And now we see all of our members are released. So they're all connected as pins at all of our joints there. Okay, I'll turn that off. Let's see here. So that's good. Layout's good. Okay. I think we're ready with everything except our section properties now. So what we need to do now is we need to define ourselves a section property that lets SAP go and select from all of the L 4x4 by anything members. And in the AISC 15 database, and same with 14, and should be for the next one as well, there's only going to be 7 of these members that are 4x4. It just changes the thickness of the member, basically.
That's the automatic part of it.
I'm sorry?
That's the automatic part.
Yeah, exactly. So, I mean, you can give it any list of members you want. For this one, I'm just saying we want them to be 4x4 angles, but we're going to have SAP pick the thickness of each of them. So we'll get to that. Just remembered, we also want to have the constraint that the bottom chord, top chord, and webs all want to be the same. So we need to group those. So we're going to select the bottom ones here. We're going to go to assign, then assign to group. So you can do that also with Control-Shift-G. We'll add a group. Add a new group here. What do we want to call that? We'll call that bottom chord. Those are all fine. So we can say OK there. Let me say OK there. And then click on bottom chord and say OK. So those are all part of the bottom chord group now. If you right click it and look at here, in assignments, it should tell you it's part of the bottom chord group as well as the group all as well down here. Now we'll do the same thing for the members of the top chord. So we'll go to assign to group or Control-Shift-G. We'll define group, add new group, call that top chord. Okay. Okay. I'll add another one for the webs while I'm in here as well. Then okay there. The top chord here, we'll say add to group. Okay. And then we'll select all the webs, Control-Shift-G, select web here, add to group, and then say okay. So if you click on a web, at the bottom here, it's part of the web group. You click on the top chord, see it's part of the top chord group. So we want to do that to know, or basically let SAP know all of these members are grouped together and we want it to pick the same member for everything in there. Make sense? Okay, so now the interesting part. So we're going to go to define, section properties, frame sections. We are going to import a new property. Okay, sorry, hold on a second. We're going to add a new property, not import a new property. So instead of import, we click add here. And we want to click this one that looks like a sheet of paper down here that's called auto select list. So we'll click on that. Okay. Sorry. Okay. First things first, we need to import those angle sections that we wanted to analyze first, and then we'll go and make an auto select list out of those. Sorry. Little turned around here. So we import first angle, AISC15. Then we'll scroll down to the L4x4s. And we see we've got 4x4 by half, quarter, 3/4, 3/8, 5/8, 5/16, and 7/16. So there's 7 shapes here. We'll select all 7 of those and then press OK to import them. Then press OK there. Okay. So now is when we add the new property, the auto select list. We'll call this whatever you want. I'll call it angles. And what we're going to do in this list of sections here on the left, we're going to select all 7 of those L4x4 angles we wanted, and then we'll add them to the auto selections on the right here. And then we'll say OK. And then we'll say OK again. And then we're going to select everything. And then we're going to assign frame sections. Then we're going to click on that auto select list we just built. It's called, mine's called angles. So I'll press OK. And then it will go and assign the angles auto select list to all of them. And by default, it's going to try the median value in that list. So the one with the medium amount of capacity. So that's 4x4 by 7/16 in this case. So that's why it says that at the start. Okay. Any questions with that so far? So we should now be ready to analyze. We went and drew our geometry, gave ourselves our restraints. We have our sections. We went and made sure every connection was pinned. We applied our dead and live loads on the top chords here. So now let's run our analysis. We're not going to run our modal case. It'll want us to save it, so we'll do that. So save that. It'll run. Okay. And we get this. Now, this is what's run initially. And this is kind of picking that initial shape it picked right out of the middle of our list. Now, we want to let SAP do design checks now. So up to this point, it's gone, okay, here's our loads, here's our structure, here's basically our internal forces and moments and shears and axial forces, all that stuff on all the members. But it doesn't know if the angle it's selected for each of these will have sufficient capacity or maybe too much capacity for all of those. So we need to go and do a design check. So it goes and does the design equations for a specific cross-section of a specific material to compare its design capacity to the forces it's calculated from the analysis here. So the way we do that for steel, in the top right here, we've got this button for with the little I section here and the drop down. You can either click the button or click here, start design / check of structure. So what this is going to do is it's going to run a design check for all of the members in our structure here. And then because we went and grouped them, it's also going to and we also went and assigned them all as a auto select list. It's going to go and pick the best, most optimal angle that works for each of the sections in our model here. Does that kind of make sense? So it goes and runs the design checks to check that that section is going to have enough capacity for the loads on it. And because we gave it a whole list to pick from, it's going to pick the one that's closest to capacity, but still okay to optimize it. And because we went and put our members in groups, it's going to pick the member for the worst case scenario in the whole group, basically. So it'll size the whole group to make sure it can meet the demands of the loads within that group. So when we've designed it, it gives us something looking like this. So we see we've got L4x4 by quarters on the bottom chord and 4x4 by quarters in the webs. I believe those are the smallest sections we have. And we see, based off of the light blue color it's given us, that that's under 50% of the capacity of the angle. So these are very conservative. There wasn't going to be a whole lot of force on those to begin with. There usually isn't on the webs, and on the bottom chords, that's pretty okay. And then it's picked an L4 by 4 by 3/4. Okay, I see what's going on here. For those and 5/8 for those. Okay, let's see. Okay, I think there's one step here. Give me just a second. Oh, so up in the top here to get it to consider all the groups together, because you see what's happened here in these top chords. It's assigned these ones right here to L4 by 4 by 3/4, and these ones to L4 by 4 by 5/8. So these are a little bit thinner than this one, but we want everything in the top chord to basically be the same. So we need to tell it which groups we want it to consider to be together. So in here, we're going to go and select design groups. And we're going to select bottom chord, top chord, and web. Add those to the right here, then say OK. And then what we're going to do here is click iterative steel frame design. We'll just click on the I section again. So the start design / check a structure, and it'll check everything again. And you see this time it's given all of these as 4 by 4 by 3/4. So they all work for that worst case member here. Does that make sense? Okay. Sorry, it's been a little bit since I've done design here. Okay. And that's all of the analysis and then design we wanted to look at. So let's look at the deliverables here. First, we want the steel design sections selected by the analysis. So we've got those right there. That's what we get right after we click on this. So you just start design, check a structure. That gives you the design sections it's picked. Second, we want the steel PM interaction ratios. So this is basically a ratio of the axial and moment demands to capacity of each of our sections. And we want this to be a fractional value. We want there to be less demand than there is capacity. So if it's less than 1, that's good. The closer it is to 1, the better, because that means it's a more efficient design. And these PM ratios, they're taking into account our load amplification factors and our strength reduction factors in design. So we will do that by going in the dropdown here, going to display design info. It's kind of offset on its own here. And then the first one here called PM ratios, colors and values. Keep that selected, press OK. And we see instead of the shapes here, it's giving us basically values here. And these values are the ratio of how much capacity, or basically how much demand is being required of the capacity for each of these elements. So they're all under 1, so they all pass. So this is a good design. Any questions on that? Cool. So if any of them turn red here, they'll have a PM ratio greater than 1. And basically, it'll mean, in this case, that you haven't given it any sections to choose from that can handle the forces that are on that member. So you'll need to go and investigate that further and go and refine your design, maybe find another section that can work with that, or change around the capacity or change around the configuration there if you need to. Okay, so those are the first two. So those are directly from the steel design that SAP's doing. Next, we want to find the reactions for each support with values and arrows for design combination DSTL2. Now, when we run a design check, it goes and generates some combinations and puts those in the background. So we'll go and see where DSTL2 came from. So, but first, we want to look at the reactions for each support with values and arrows for that combination. So we'll go to joints, and then here we had the dead and live that we looked at, but now we've got DSTL 1, 2, 3, and 4. We'll click on 2, say OK here. And we see these are the reactions for that design combination. It's symmetric, so that's all good. Okay, so next we want to look at the deformed shape for that design combination. Okay, so we'll go and click on DSTL2 there. I'll put that back to automatic. That's all good. So we'll press OK there. And that's our deformed shape. So we see these are all behaving pretty linearly, which is good. That means that the pin behavior is working at each of our joints. Next, we want to look at the axial diagram for design combination DSTL2. So we'll go to frames, cables, tendons, click on axial here, click on DSTL2, show values, say OK. Here are our axial forces for each of those members. And as you can tell here, because we have distributed loads on these top trusses, we have a non-uniform axial load here. So the further down we get on our truss, the bigger the axial load gets because we have more and more distributed load feeding towards it. And in each of our web members here, those should be pretty uniform. They'll be slightly non-uniform due to self-weight, but pretty uniform mostly. So they all should be trapezoidal. Okay, then we want to look at the shear and then the moment. So those are all easy. For this one, we'll do shear 2, 2. So those are our shear diagrams. So these are all basically 0. These are all just due to self-weight of those members. And we've got the shear diagrams from all of these, and that should make sense to y'all because it's basically a uniform load. So this is the shear diagram for a uniform load. And then the moment diagram, you should be able to guess what that'll look like. Should be a parabola. So click on moment 3, 3. And what do we get? We get a triangle. Why do we get a triangle like this? It's because SAP has only calculated one intermediate point for all of these. So it only gives us these 3 points for the moment diagram. If we want to get the actual parabola, what we need to do here, let's go and select all these. We'll go to define, assign frame output stations. And then the minimum number of stations here is 9. So I'll say select OK on that. Then I'll go and rerun this analysis. Done that. I'll go and run our steel design again. Get all those again. Those are all still good. Let's go and look at our moment diagram again. So now we've made sure it evaluates at least 9 points along the member. So we go and get that full parabola now.
How you want it to be I report?
It would look best that way, yeah. So if you know it should look like a parabola, double check the output stations to make sure it's giving you the full picture. So
change anything on sign frame output?
I'm sorry?
Oh, because you get a something.
Right, yeah, I selected all of them. I made them all. I set the output station to 9 of them on all of them.
Oh.
I mean, if you look at shear, it'll be the same diagram shape. It's just going to have more of these lines in the middle because it's evaluating at more output stations there. Yeah, so I mean, that's one of the reasons it's good to check your models. If you just gave that as your moment diagram, that would look like someone put a bunch of point forces right in the middle of all of those joints instead of having a uniformly distributed force on those. So it's good to double check your models doing the right thing, basically. Okay, any questions on any of that?
Both of you. Next Thursday or the following Thursday.
So they're both due on December 1st. I don't want anyone needing to turn this in on Thanksgiving. So Lab 9's due then as well, and this Lab 10 is due on the 1st as well. Uh-huh. All right. Any other questions on this? Cool. Well, thanks for sticking around. Hopefully it's a interesting lab for y'all. I know these last couple things are always interesting for me. It saves a lot of time being able to import things, and then it also saves a heck of a lot of time being able to double check your design in SAP as well. And I'm sure next semester y'all like that as well.
Do you have a lab for structural analysis too?
No, there's no lab for structural analysis too.
Okay.
We'll be doing a bit of programming and stuff as part of the class to go and write some software to go and do some of that analysis ourselves. But no, there's no lab section or anything.
Hopefully nothing too hard.
No,
Programming wise.
it's not that hard.
Okay.